Continuing, here are some applications of eutectics. So in solder, 67% tin and 33% lead by mass melting at 183 degrees Celsius. Eutectic formed by 23% NaCl and 77% H2O by mass melts at negative 21.1 degrees Celsius. Salt is added to ice under isothermal conditions, for example, when spread on an icy road. The mixture melts if the temperature is above negative 21.1 degrees Celsius and the eutectic composition has been achieved. Salt is added to ice under adiabatic conditions, for example, when added to ice in a vacuum flask. The ice melts, but in doing so, it absorbs heat from the rest of the mixture. The temperature of the system falls, and if enough salt is added, cooling continues down to the eutectic temperature. Eutectic formation occurs in great majority of binary alloy systems and is of great importance for the microstructure of solid materials. Although a eutectic solid is a two-phase system, it crystallizes out in a nearly homogeneous mixture of microcrystals. The two microcrystalline phases can be distinguished by microscopy and structural techniques such as X-ray diffraction. Eutectics analysis. Thermal analysis is a very useful practical way in detecting eutectics. How it is used can be understood by considering the rate of cooling down the isoplet through A1 in the previous figure. So here in this figure, we can see the cooling of this substance. So we have here A1 to A5. This arrow represents your temperature, and this one your composition, and this one is the time. So from A1 here, the liquid is cooling. So it is represented by this area, the green one. So from A1, the liquid cools steadily until it reaches A2, when B begins to be deposited. So here sa A2, we can see, paglabot sa A2, there is this brown colored area where the B begins to be precipitate. So the cooling is now slower because the solidification of P is exothermic and retards to the cooling. So, it becomes slower na ang iyon na cooling. So, naglawig ang time sa pagpanaog sang temperature as we can see in this slope kay gaamat-amat na siya solidify. So, next, when the remaining liquid reaches the eutectic composition, the temperature remains constant until the whole sample has solidified. So, paglabot sa A3, nag-constant na ang temperature. So, this region of constant temperature is the eutectic hold. So, here we can see in this white region, the eutectic solidifying. So next, if the liquid has the eutectic composition initially, so here, for example, the E, it has a eutectic composition na liquid, so the liquid cools steadily down to the freezing temperature of the eutectic. So as we can see, in this portion, nagdiretso na sa dayon sa eutectic solidifying. Unlike in this liquid here, nag-agi pa siya sa different state and hasta nakalabot siya sa solidifying sa eutectic nga halt. Okay. So, if a liquid is has eutectic composition, gadiretso na siya dayon solidify. So next, then there is a long eutectic halt as the entire sample solidifies, like a freezing of a pure liquid. So here we can see if a substance, or if a liquid rather, has a eutectic composition, it has longer eutectic halt than this substance. So that's it for the eutectics analysis.
In this illustration of the phase diagram for the binary system silver tin, The regions have been labeled to show which each one represents. As you can see on the right, the diagram tells us that when a liquid of composition A is cooled, solid silver with dissolved tin begins to precipitate at A1, and the sample solidifies completely at A2. It means that silver began to cool first, thus silver plus liquid is present in A1, and when the sample reaches A2, both tin and silver solidifies. Monitoring the cooling curves at different overall composition gives us a clear indication of the structure of the phase diagram. The solid-liquid boundary is given by the points at which the rate of cooling changes. The longest eutectic halt gives us the location of the eutectic composition and its melting temperature.
Now that we have learned about the concepts, theories, and applications of eutectics, we are now ready to learn about reacting systems. These systems, as the name suggests, undergo reactions, unlike the preparation of alloys in our previous topic, which only includes the mixing of two solids or metals to form alloys. It is defined that many mixtures react to produce compounds. For example, for group 13-15 or 3,5 semiconductors, such as the gallium arsenide system, which forms the compound gallium arsenide. 3,5 semiconductors such as gallium arsenide offer materials property advantages over silicon, such as increased carrier mobility and direct band gap, which may be used for microwave and optoelectronic applications. Applications such as monolithic microwave integrated circuits, microwave frequency integrated circuits, infrared light emitting diodes, solar cells, laser diodes, and optical windows. Although three constituents are present, there are only two components because gallium arsenide is formed from the reaction gallium plus arsenic yielding gallium arsenide, which means that gallium arsenide is composed of the same elements that are reacting to form it. To illustrate some of the principles involved, consider a system that forms a compound C that also forms eutectic mixtures with the species A and B, which will be illustrated in the next slide. Now, a system prepared by mixing an excess B with A and consists of C and unreactive B, where B in excess is therefore the excess reactant, with A is the limiting reactant. So this system is a binary BC system, which in this illustration, as seen on the right, is supposed to form a eutectic. The principal change from the eutectic phase diagram in figure 5D1, the first figure, which is here illustrated above, is that the whole of the phase diagram is squeezed into the range of compositions lying between the equal amounts of A and B. Therefore, the mole fraction of B is equal to 0.5 and marked C in the figure 5D.4, which is here below, our reacting system diagram, and pure B. So this whole diagram is a compressed or squeezed version of this segment or part of our reacting system. The interpretation of the information in the diagram is obtained in the same way as for figure 5D.1. However, the solid deposited in the cooling along the isoplate A is the compound C. So to trace that, let's look at the isoplate. So first, A sub 1 to A sub 2, where the system enters the two-phase region where liquid plus C, where pure C begins to solidify and the remaining liquid is richer in B, because B is in excess and lesser than A, since A is the limiting reactant. Now, we have A sub 2 to A sub 3, where more solid C forms and the amount of solid and liquid are in equilibrium. At this stage, there are roughly equal amounts of each. The liquid phase is richer in B than before, and its composition is given by B3, which is seen in the diagram, because some C has been deposited. The next is A sub 3 to A sub 4. At the end of this step, there is less liquid at A3 and its composition is given by E, which is the eutectic point. This liquid now freezes to give the two-phase system of pure B and pure C, where C is the product of the reaction. At a temperature below A sub 4, there are two solid phases, one consisting of C, the product, and the other of B, the excess reactant. The pure compound C melts congruently. That is, the composition of the liquid it forms is the same as of the solid compound, which means that when C is formed from the reaction between A and B, if you melt C into its liquid form, it would also be compound C. For example, we have gallium and arsenic, and which yields gallium arsenide. If we have gallium arsenide as our product, which is solid, and if we melt gallium arsenide, it is still gallium arsenide. So, that's all for our reacting systems.
Let us move on to incongruent melting. By definition, incongruent melting is a melting wherein a phase melts to a liquid with a composition different from the solid and produces a solid of different composition to the original solid. In short, it is said incongruent kay once i-melt mo ang solid, like for example this alloy Na2K, the chemical composition produced is not the same as Na2K anymore. It means it is already a different compound. Look at the diagram. The diagram shows an example of a compound transformation, a reaction of a liquid phase and a solid phase to form a second solid phase during cooling. This diagram also explains that Na2K exists only at a solid but not in a liquid phase. For the physical interpretation of this diagram, in A2, as labeled here, it can be seen that it is reached in solid Na. So when the temperature lowers, or as A2 approaches A3, a solid solution rich in Na is deposited. The remaining liquid is richer in K. A2 approaches A3 here. On the other hand, below A3 here, it is labeled that it has a solid Na2K and a solid Na containing some K. It means that the sample now is entirely solid and consists of a solid solution rich in Na and solid Na2K. Now, let us go with isoplete through B1. When we say isopletes, it indicates a region wherein a component is constant. In this diagram, the isopletes is here from B1 to B4, meaning the components in this region is the same respectively. For the physical interpretation, as B1 approaches B2, it can be seen that no change occurs here. The change occurs only when the phase boundary is reached at here, at B2, when a solid rich in Na begins to deposit. As B2 approaches B3, a solid solution rich in Na deposits, and here at B3, the reaction occurs to form Na2K. It is when the potassium atoms is diffusing into the solid sodium. At B3, when you try to zoom in the diagram, it is displayed that the three phases are in mutual equilibrium here, meaning there is a liquid, the compound Na2K, and a solid solution rich in Na. The horizontal line here is representing this three-phase equilibrium is called peritectic line. At this stage, the liquid Na or potassium mixture is in equilibrium with a little solid Na2K, but there is still no liquid compound. As B3 here approaches B4 here, or as the temperature continues to lower, or as cooling continues rather, the amount of solid compound increases until here. Before the liquid reaches its eutectic or easily melted composition. It is then solidifies to give a two-phase solid consisting of a solid solution rich in potassium and solid Na2K. Moreover, what I have discussed in the previous slide is the formation of second solid phase during cooling. But if the solid is reheated, the process is reversed, and Will then explains the concept of incongruent melting, in which a compound melts into its components and does not itself form a liquid phase. And that would be the end of our presentation. Thank you.